known as Itay from Cabiran. Itay joined Cabiran in 2002, and he's the Chief Technical Officer. So here's Itay.
Thank you, Nick. I'd like to thank all of you for the opportunity for the SAI to present one of my papers. Today I'm going to take you for a short tour in Cabiran, which is an investment casting aluminum foundry located far from here in Israel. We'll speak a little bit about increasing our capacities, capabilities, and our cost reduction activities we did over the past 4 years. Running some upgrade process through our production line, trying to gain all these 3C requirements that we set to ourselves. So, with a short introduction to the process of investment casting, we all know that in investment casting has not been involved much from its original beginning. Practically what we do is we have wax injections, wax assemblies, shelling, dewaxing, and pouring into hollow ceramic shells, which was for the past, I think, couple of thousands of years. Complex geometries combined with relatively small production runs became more characterized to our foundry. Simple mistake in one of the steps could lead to a loss of a part, the assembly, or usually the whole batch, resulting in significant impact in our cost deliveries. The combination of labor-intensive operations and long manufacturing cycles, and trying to manage all those variables up there, and elaborating under the pressure to meet the delivery commitments to our customers, lead our industry to a very conservative approach, which practically means that if it works, just don't touch it, and if you want to touch it, stay out of us. So all those combinations together brought Cabiran to a certain situation where we were thinking maybe we're the best, but maybe we're not. Today technology evolved in the past 10 years, and I can emphasize some of the stuff that evolved around us. I think one of the main out of them is the CAD programs. If you're familiar with the prints and the blueprints and drawings which used to be hanging around back at the 80s or 70s or even before that, today everything goes in a CAD systems. So simple parts like that one, which you can assemble in a big tree, lots of parts, and be very efficient, not longer in our field. We practically lost it somewhere else, but what we have left with is those CAD complex subsystems combined all together in one part, thick and thin walls, lots of undercuts, geometries, led us to one part per assembly, and long manufacturing, injection and assembly, and the geometry just going heavily complex from day to day. In addition, or at the same time, higher quality demands arise in the market. We're all familiar with the ISO 9100. Now comes the net cap, requiring even higher quality. And then on the same token, with the surface finish, if we were talking about 130, 120 micro-inch back 10 years ago, most of our customers requiring today between 190 micro-inch surface finish on the cast parts. So how do you get all that in the best foundry you can find? Then increased demand in airframes application for use of the A200 series aluminum alloys brought a very non-friendly aluminum type of alloy into the process. So if 30 years ago or 20 years ago we've been casting approximately 2 or 3 tools using the 200 series, today Cabiran is actually putting it on a weekly basis. Unfriendly alloy that doesn't like to be poured. Market demand for cost reduction initiatives from the foundries, and instead for the price to go up, the price tends to go down. So here we are again, is what we used to make, and today this is what they want us to make, approximately the same price. So, what we did is, we decided we're going to have to run some of the methods that are in the market, and probably everybody are familiar with the RDMIC process and principle of know-how. Practical know-how applying the process. It was critical to Cabiran to start thinking, do we actually know everything? Do we actually can fulfill everything that we think we are making? And the first step is recognition. I don't know if everybody's familiar with the R before the DMIC, but there is an R, and the R is recognition. And the recognition we had to say, and we had to put ourselves in front of our eyes, was like, we're 40 years in the business, yet we might not know everything in the business. And once we jumped that step, and we were able to say, okay, we're not the best, and maybe there's some stuff we don't know to make, we moved into step number 2, which was defining the goal that we're looking for, and that's how we came up with the 3C idea. So the 3C means that if we'd like to increase our capacities and our capabilities, but at the same time we would really like to reduce the costs, which not all the time works, but it's a good idea to think of. The third step we did is taking some measures, like measuring the foundry itself. And we found 2 items that I can just say is an increase in production will result in increasing scrap rates. I'm pretty sure most of the foundry here are familiar with that phenomenon. Let's increase production, let's get on to second shift, let's put more shells on the hangers, but the scrap keeps going up. Then at the same time, we found out that our FAI development process for new tools is taking more than 6 months. Going into it and trying to realize how come, we realized, well, we're running iterations back and forth, more gates, more chills, less chills. We passed the FAI, but we're not really manufacturing. Then on step 4, which I will discuss a little bit more and further in those slides, was running the improvements. So we went into our process departments, which are, I can say, the 3 process departments in the foundry. The first of all, in the heartbeat, was the foundry itself, trying and gaining better control on our melts. And then the VAX assembly room, in which we were trying to look at our methods and practice in gates and runners, how we assemble actually. And then final, and maybe the most intimidating, is the shell department. Going in slurry compositions, the drying cycles, the layers, the amount of layers, the sands, the refractories, everything we've been using in the past more than 20 years, I guess. Then finally, getting control of another thing that we actually did, and actually instituting a production continuous improvement team to monitor those changes we ran. So I'll take you a little bit inside, and we're going to dive straight into the foundry, and I'll give you some of the topics, the stuff we did in the foundry department. So the first observation that we recognize is that our main phenomenal defect is a microshrinkage. You can see on the pictures on the left, the lamellas partially structure modified, which you can see the microshrinkage behavior even worse. And then on the right, you can see an acicular structure, which is an unmodified structure, but at least it's stable. And you can predict what's going to be the outcome. So, we went a little bit deeper into it, and we found out that our degassing process and the cycle were undefined. Practically the workers, the foreman and his guys were doing it on a daily basis, but they were the only ones that knew how to do it. And we spoke about it in the morning. If one of them should go, we don't know even how to operate that. Now we found out variation in training in the personnel itself. One of them was doing it for 20 minutes, while the other one was doing it for only 10. They were playing with flow ratios of volume. They were doing different stuff, nobody knows what. Misinterpretation of microshrink defect as gas porosity would have sent us back to degas the furnaces right before we were casting in the very same day. So we're finding ourselves degassing, back and forth degassing, and nothing else. Excessive foundry control and the inspections became a daily practice, because once you don't know what exactly you're doing, you just go in X-ray, and you run FAI on everything you do. So now it's become pretty hard to cast a lot of parts per day, okay? Because you need to wait from the morning till 10, 11 o'clock to get an approval that the casting scrub because you degassed in 6 in the morning. Now you have already gas in 11. Constant changes of shell and melt temperature became a daily practice in Cabiran, and we were playing it as a common practice. Found out that this consumed a lot of the day. Change the temperature, pour another one, go for foundry control. Maybe we're doing it a little bit wrong. So, what we did, started improving the process. First thing was encounter the micro-shrinkage phenomenon. We decided to increase the phosphorus use that we were using, mainly because phosphorus is not like silicon. Once it magnetes it, we get a cyclical structure, which is unmodified structure, but at least it's something that is stable. And we will know, and we will be able to monitor this structure and solidification behavior day after day. Melt control. We installed a portable metallurgical inspection unit combined with a thermal analysis unit that can be applied in the foundry and can give us a good, quick reading on the modification level that we have per melt per day. Instead of going and checking the casting itself, we were starting to check the furnaces themselves. Electronic gas level detection gave us an inspection for hydrogen level before we were pouring. So meaning when you degas and when you run the measurement, you know that gas is not your issue. System are all fully electronic. You can see some of the pictures illustrated here of the thermal analysis we've been using and the hydrogen level detection unit that we've been using. And those very same machines, which are electronic operated and can be repeatable, gave us a very, very good view on the actual melts we have and allowing us to look for the problem somewhere else. Degassing improvement process. We stopped utilizing our old method and technique of degassing just because that we had a very old machine. Obviously in the foundry nobody likes the changes, so it was the best machine you can buy. But turns out it's not the best machine you can buy, and it turns out it's a very, very complicated machine to operate. And each one of the persons that were operating that was doing it differently than the other. So we introduced the foundry with a fully automated system. This kind of system that you push a button and it does the degassing process every day, the same thing. The same ratios, the same cycle time. Same rotary, same RPMs. We changed the sequence of degassing process and performed only prior to pouring. I don't know what you've been doing in your foundries, but we've been doing degassing also the day before. We had like traditionally degassing in the night. Nobody knows why, but that's what they were doing. So changing all that is pretty, it's not easy. It sounds easy, but it's not really easy. Taking people that did it for 20 years and telling them, well guys, you're not doing it right. And the idea behind it was to gain more and more success in the process, allowing the personnel in the foundry itself to gain more confidence that the changes we're running are actually working for them. We developed the correlation data using result and methodological tests. You can see one of the simple sample we did, which is very, very simple, of showing the people how much gas do they have in the degassing process using the old method and how much gas they actually have using the new system. So once you can see it visually, you don't need graph. Well, we established the correct degassing cycle, and finally, we defined the gas level number. And that number, which the machine gives them every day, if they meet the number, then degassing is fine. You don't have gas. You have something else if there's something wrong with casting. So, results. But the new degassing process and control allowed us to determine that the defects observed in the NDT were definitely micro-shrinkage indication and not gas porosity as we're used to. The phosphorus use enabled us to be sure that the same solidification behavior is happening and occurring every single day. Meaning that if we have micro-shrinkage phenomenon, it's not because playing with temperature and it's not because of gas. It could be assembly. Phosphorus. The benefits that we gain out of it is, first of all, we got 25% reduction in degassing cycle time, which increased our capacity just by allowing more spare time their day, so we can pull more parts. Thermal analysis ruled out micro-shrinkage as a result of melt. Allow us to be more free of thinking and trying to look for the problem somewhere else. We called it freed up engineering to focus on back assembly setups. 60% decrease in the the melt shows, the thermal analysis shows the melt is non-modified, and if the degassing process shows that there's no hydrogen, there's nothing you can do. You can pour, but there's no changes for you to do on the very same day. Process is fixed, allowing us to cast more per day. The team was operating more freely. They were more calm. There were not much that the people would need to worry about. The equipment gives them the job, does the operation, gives a number, it works. Vax assembly. The first observation we've been seeing is that our vax assembly is based on the plaster mold process. Why? Because Cabiran was founded on a plaster mold method, and we've been a plaster mold foundry for the first 6 or 7 years. And when we just formed back in 1969, the pattern mounting process was labor intensive, resulting in reducing the output. Now you have to put lots of gates, lots of runners, different gates. In parallel, we had a never-ending development cycle. All the parts adding more gates, cutting gates, more gates, cutting gates. You put the gate here, then the shrink on the other side, right? So let's put another gate on the other side, but the shrink now is up. So let's take off some of the temperature, so that you go non-fit. So just hopefully the customer doesn't hear about it. High rate of part defects without understanding the root cause, or let's say understanding the practical of the root cause, led us to a very weird assemblies with weird parts on them. Some of the examples, you can see 17 feed gates on the left picture. On another small part, you can see on the right side more than 6 feed gates on a very, very small valve, 4 parts per assembly. I wouldn't tell you the amount of scrap because I don't want to embarrass myself, but the 4 parts per assembly and 7 feed gates. So, the analysis came. We found that the old vax assembly practice, which was gate and chill practically, putting lots of gates and trying to chill at the same times on the other side. How we come to it? Well, first of all, what we did is we had a method. We were putting the gates in the tools even before we ran the FAI. It was like a system. The engineer gets the 3D model, puts a gate on it because he knows, and then you make the tool, you get the part, you got like a, I don't know, porcupine stuff sticking out all over gates around it, and now you start running with it. So now you start cutting gates, adding gates, nobody knows exactly what the part means. Multiple gates were used mainly to address the non-field defects which we were encountering, mainly in pinhole castings. Then those non-field defects were caused by low shell and pouring temperature, which we were trying to avoid the micro-shrinkage and the gas porosity phenomena, which led us to a low pouring temperature inhabited feeding of thin walls, which resulted in micro-shrink. So, what we did, we changed the assembly concept. And again, changing the assembly concept in a foundry after 40 years, it's not something you come and do. You have to prove. So you need to take the most horrible part that goes in the line that nobody likes to assemble, nobody likes to pour, nobody likes to inspect. The NDT guys usually tend to be sick of that very same day because they don't want to be responsible for the weird stuff they can see on the X-ray photos. And we said, okay, let's minimize the number of gates and put it on the first setup. Let's put the minimum gates we can. Okay, so we put only a couple gates to hold the part so it won't fall in shell. We get on thick sections, and we know we don't touch the thin walls. Modify the vax cluster frame to improve the drying process of the shed, allowing the fans, allowing the humidity to flow through the parts and dry it better. We took the first top 20 and they identified those 20 volume scrap generators, and we start running on them with an FMEA method, practically trying to realize what the problem is. So now we employ a new design method and based on a lesson learned that we've seen the first one. We plug the gates in the vax injection tool only after the FAI approved. Then we remove all the chills. Design the vax assembly to be more industrialized, meaning that we were standardizing our runners and our gates, top and bottom frames, feed cups and filters, so everything will be the same. It doesn't matter what the size of the part, we're going to make a top and bottom And most important, we're going to put as least gates as we can on the first setup, even if it means that it will go scrap. We don't care. We want to see how the aluminum flows, how it solidifies, what are the actual problems. One of the things that I didn't put in my presentation, it's also on the foundry standpoint, is unifying the temperatures we've been using. So by doing so, we're not changing any more our temperatures of the preheat ovens, and we're not touching the temperatures of the furnaces themselves, meaning that it's easier to degas and easier to maintain the melt on the daily routine. So, recognition that our established method and practice were no longer relevant to our current foundry process, which was maybe they were relevant back in the 70s or 80s when we had small parts. So it's a small part, put it in and get it over with. Now we have big parts, and you can't keep on doing that method. So, like we were saying, ring became 5 feeding gates, or those small valves became 8 parts per assembly instead of 4, with only 2 feed gates per part. Now they're drying better. They drain better, much easier to process, much easier to clean. Obviously drying off half of the gates or even less. And most importantly, it gives us an easier view on the casting behavior. So now we know if those parts get micro shrinkage or gas porosity, then we should go and check the process. Somebody didn't do the degassing process properly, maybe they are out of atom. Nobody knows. So, achieving the first 2 C's capacity. We achieved 35% capacity increase in wax mounting and metal pouring all together just by doing all those things I just showed you. I'm trying to give a little bit more idea of the vast change we had in gating, and I can say we achieved an average of 60% reduction in the number of gates on a 16-inch long electric boxes. I don't know if, I'm guessing most of you are familiar with the electronic boxes, those horrible parts that looks very simple, but they never. So those parts, which are approximately 16-inch long, reducing more than 60% of the gates, meaning you reduce a lot of labor. Putting the gates, gluing the gates, runners, aluminum, cutting them off, and blending them obviously. Capabilities. Well, reduce the setup time and develop a new sample parts by 60%. Now we're running 1 iterations, no gates on the parts. We're seeing where the problems are. Put the gates only where it's needed the most. And we're done with the iteration, and the part works. Reduce the casting defects by 30% just by actually knowing what the problems are. Modification to some of the foundry equipment and improve in the process results in increase in part size by more than 40%, just by running modification to our equipment, just by going towards a certain particular casting method, which is the vacuum process, as far as probably most of you know, allow us to increase the size of parts we were pouring by more than 40%. On the graph here, which I'm going to try and show you as minimal graph as I can, you can see a learning curve that we've been through 2006, trying to learn how to operate the foundry in our new method. You can see it was going up and down, up and down, up and down, until there's a certain curve that goes down. Obviously, the next question, yes, we are under 1% scrap ratios in casting due for casting defects also today. Okay, I wouldn't show you the graph, but it's under 1%. Gentlemen, our observation mainly was that we've been using between 9 to 10 coats of slurry, and it created a long and ineffective shedding process. We experienced high scrap ratios due to shed cracking and inclusions. Our slurry formulation had no actual connection to the material we've been using. We actually found that the formulas that we had were 25 years old. The suppliers that we've been buying for the past 10 years were changed. It's a different material, but the formulas kept on going. We've been using methylene chloride and isopropyl alcohol embedded inside the process as wash and etch process. Probably you all know it's a very hazardous process. Nobody likes the methylene chloride. Also we did. Then we found out that increasing our yield was linearly connected to our scrap ratios. You can see in the end of 2006, when we came out of the foundry process very strong and confident, we said, let's go with production. Let's move, shift it to 5th gear. Let's start moving. And that's what we got. So scrap ratio going up the roof. And shell kept on cracking and undrying and inclusions all over. And it turns out we don't know exactly what to do with the shell. So, improving the process, the first step we take is partnering with the slurry and refractory supplier that is currently today Branson Reynolds. They introduce us to a new slurry formulation and mixing refractory materials. And the main critical idea for us was actually being taken under one of the suppliers that knows the business, knows the latest upgrades, knows what goes in the market, and can give us the best support, technical support that we can find. We conducted the design of experiment process, and we identified first of all the key variables which have the greatest impact on the process. Then we recorded our scrap history just in order to be able to track it down as long as we develop. And finally, we installed a prototype shell lining to replicate the final process. The left picture can show you a very good example. I don't know if it can be seen here, but the left picture, you can see the foremost primary slurry we had. You can see the fish eyes around it, it just doesn't cover. And you can see the new slurry, how it behaves. This is something we haven't seen before. And the left side is, well, it's a little bit hard to see, but you can see the old one in compared to the new one. You can see a very straight line. And here you can see those dress tights on the bottom. Doesn't drain. So, on shell results, we reduced the number of slurry sands codes by 40%. We went down from 10 to 6. We reduced the shell cracking during dewax by more than 60% just by applying a new backup system. And all of a sudden, those cracks we've been using to rework in slurry, we actually had a person that was working on this foundry as a rework guy. He was like the expert guru of reworking shells after dewaxing. Okay? We reduced the silicon sand usage that we've been using by 50% just by eliminating one primary coat of the process. And I think one of the most successful process we were able to implement is getting rid of the methylene chloride process and actually stop washing and etching our wax assemblies, which cut the process even more. So, how do we achieve this third C in cost reduction? Best thing to see is in shell. Because when you take off full coats of the shell, you can see a reduction in refractory materials because you less floors, sands, and binders consumption. Reduction in energy consumption, obviously, because you dry and you build faster. Reduction in cycle times when you reduce the dipping and drying cycle from 72 hours to 53 hours. And then finally, reduce the labor, which usually costs a lot. I bet you didn't know. So, you have to excuse the computer here, but you can have to believe me, these are quarters. It was a long process for shell. It's not something that took us a year. It took us a little bit more than 2 years in order to get from here to here. We're still on a learning curve today. There's still a lot to do. There's still a lot of things we would like to upgrade. There's still a lot of fine-tuning we need to do. We have multiple different parts that are going on the line. If it's a lot of pins, electric chassis, along with big manifolds, wide wall, thin wall, all these parts need to combine into one process of shell. But I think the results and the lines are speaking for themselves. In summary, Cabiran has increased its production output through 2007 and 2009 by 35%, which was one of our main goals and was one of our main ideas. We developed the production continuous improvement team. We built the production continuous improvement us down what do you think we should make better. And if you think something needs to be better, then you come and ask with us and be one of the part of the team. The control and monitor daily manufacturing activities by making those people active in developing and re-evaluating. They were more active in line, trying to look for solutions, not only the engineers. And finally, identifying the opportunities for productive improvements, which they have come up with, and we're just embracing. Again, there's not much to understand from the line, apart from that's 2006, the first quarter, and that's the last quarter of 2008. The line in 2009 is going a little bit like that, and you all know why. So, I think that was on tip of the edge of what Cabiran did the past 4 years, and we're still going to